You have lived your entire life beneath a star, and no one, not once in the history of our species, had ever seen its poles. Not until 2025. Scientists photographed the sun's south pole for the first time that year. And what the images showed contradicted almost everything textbooks assumed about how a star organizes itself. The magnetic field at the pole was not one clean polarity. It was a checkerboard of both polarities, tangled together. The pole completes one rotation in 38 days, while the equator finishes in 25. A gap of 13 days that never closes. And sound waves traveling through the sun's interior revealed a river of plasma moving in the wrong direction entirely. Tonight, we go through 4 discoveries about what happens above and below the surface of our star. The pole no one had seen, the interior current that shouldn't exist, the 2 hemispheres falling out of sync with each other, and the failure that could end 400 years of prediction. By the end of tonight, you'll understand exactly why the star you were born under is stranger than the one described in any classroom. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. For 400 years, every photograph of the sun was taken from almost the same angle. Every observatory, every satellite, every human eye that has ever studied our star has done it from roughly the same flat plane, the same equatorial belt where Earth and the other planets circle. Not by choice, because nothing we had ever built could reach any other angle, until Solar Orbiter left the plane. In 2025, the spacecraft used the gravity of Venus to bend its own path upward, tilting out of the flat disk every planet moves through, and looked down at the sun's south pole for the first time in the history of our species. What came back did not resemble the tidy diagram you may remember from a textbook. One clean pole positive, one clean pole negative. Field lines arcing peacefully between them like a bar magnet resting on a desk. The south pole looked less like a magnet and more like an argument. Patches of one polarity sat directly beside patches of the other, tangled across the same stretch of plasma, refusing to resolve into a single direction. Imagine opening a compass and watching the needle try to point everywhere at once, north, south, and every direction between, with no side ever winning long enough to settle. You have spent every year of your life beneath a star that could not, in that exact moment, decide which way its own poles pointed. You never felt it. Nothing about your ordinary Tuesday changed, but something in the machinery above your head was caught mid-argument with itself, and nobody on Earth knew it until a camera finally flew far enough away to look back down. The reason nobody had seen it sooner has nothing to do with ambition and everything to do with fuel. Every spacecraft ever launched toward the sun starts out riding the same momentum Earth already has, moving through the same flat plane the planets share, because climbing out of that plane costs more energy than almost any other maneuver in orbital mechanics. Solar Orbiter did not brute force its way out. It stole the tilt from Venus, trading a series of close flybys for a slow, patient climb, 7 years from launch to its first clear look at the underside of the star. Patience, in this case, was the only currency that worked. A spacecraft named Ulysses had flown over both poles once before, back in the 1,990 seconds, but it carried instruments built to taste the solar wind passing by, not to look backward at the surface producing it. It told scientists what the pole's wind felt like without ever showing them what the pole's face looked like. Sampling the exhaust and photographing the engine turned out to be 2 entirely different kinds of knowing, separated by 3 decades. The engine that keeps this star alive might not be where anyone thought it was. Hold that thought. We will return to it more than once tonight. But the tangled field was not the strangest part of what the pole revealed. The pole does not even keep time with the rest of the star. The sun does not rotate as a single object. A rocky planet turns the same speed everywhere on its surface, the equator and the poles completing one day together, locked in step. The sun is a ball of plasma, held together by gravity rather than a rigid crust, and every layer of it is free to turn at its own pace. At the equator, one rotation takes about 25 days. Near the poles, the same rotation takes closer to 38. Scientists call it differential rotation, and it has been measured since the 19th century by tracking sunspots as they cross the visible disk. Dark blemishes dragged along by the plasma beneath them, timed like the hands of a clock running at two different speeds depending on where you place the watch. If you tracked a single sunspot near the equator and another near the pole starting on the same day, the one at the equator would complete its lap and begin a new one before the polar spot had finished its first. The gap is not small. Over a single rotation, the equator can lap the poles by roughly 13 days. Hold that number for a moment. Over a year, that difference compounds into an entire hemisphere of the star, falling out of step with itself over and over, without ever correcting. No planet in the solar system behaves this way. No moon, no asteroid, nothing solid enough to hold a fixed shape does this. Only a body made of plasma, thin and hot enough to flow rather than hold form, can turn at different speeds depending on latitude and stay in one piece while doing it. An English astronomer named Richard Carrington noticed the pattern first in 1859, tracking sunspots across the disk for years before realizing that spots near the equator kept lapping spots closer to the poles, as though the surface itself refused to agree on what a single day should mean. He had no way to explain it. He only had the patience to notice it. Sketch after sketch, rotation after rotation, until the pattern became impossible to dismiss as measurement error. Scientists have never fully agreed on why the gap holds steady, rather than smoothing itself out over billions of years. The way friction slows a spinning top, something inside the sun keeps replenishing the difference. Decade after decade, cycle after cycle, something is feeding the imbalance instead of letting it settle. The gap does more than embarrass the diagrams. It winds the sun's magnetic field lines the way you would wind a rubber band by turning one end faster than the other, stretching them from simple north-south arcs into long spirals that eventually snap, releasing the energy behind a solar flare. The uneven rotation is not a side detail of the story. Increasingly, scientists suspect it is the story, the raw mechanical stress that the rest of tonight's discoveries are reactions to. That something lives beneath the surface, in a place no photograph, however far the camera travels, will ever be able to see. A clean magnetic pole is not a cosmetic detail. It is the seed of everything the sun projects outward, across a bubble of influence roughly 100 astronomical units wide, reaching past every planet, comet, and speck of dust bound to this star. The polarity at each pole shapes what scientists call the heliospheric current sheet, a vast, wrinkled boundary spiraling outward through the solar system, like the frill on a ballerina's skirt, splitting the magnetic field into a northern half and a southern half. When the poles are clean, the skirt holds a simple shape. When the poles are caught mid-argument, tangled patches of both polarities side by side, the skirt does not know what shape to hold. The boundary folds unevenly. Spacecraft crossing it have reported crossing the same magnetic boundary several times within a single orbit, flickering between north and south, the way a radio flickers between two stations that are both, somehow, still broadcasting. Not gradual, not orderly. This is not a flaw in our instruments. It is the actual physical condition of the field during the years surrounding solar maximum, the peak of the sun's activity cycle, when the old magnetic order has broken down and the new one has not yet arrived. For roughly 2 to 3 years out of every 11, the star you depend on for the shape of near-Earth space does not fully know which way it is pointing. You live inside that skirt. Every satellite in orbit, every polar airline route, every compass on Earth answers, indirectly, to a magnetic field shaped by a boundary the sun itself cannot currently hold steady. This is not an occasional inconvenience. Earth crosses that folded, wrinkled skirt every 27 days as the sun rotates beneath us. and every crossing can jolt the local magnetic environment enough to matter to a satellite operator, a power grid engineer, or a pilot rerouting away from a polar corridor during a solar storm. Most of those crossings pass unnoticed by anyone who is not paid to watch for them. A few do not. Genuinely, nobody can say in advance which crossings will be the quiet ones and which will not, because nobody can yet predict how many folds the skirt will hold at any given moment, months ahead of time. The forecasting models that try are working from a shape that is still actively arguing with itself. Picture the difference between a flag hanging still on a windless day and the same flag caught mid-snap in a gust. And you have some sense of the two states this boundary moves between. A calm current sheet ripples in slow, predictable waves. A current sheet shaped by a confused, tangled pole snaps and folds unevenly, and a satellite passing through the fold at the wrong moment can find its surrounding magnetic field reversing direction 2 or 3 times in the space of an hour, faster than most onboard systems were designed to track. But the shape of the skirt was never the only mystery living at the pole. There is a hole up there too, an opening in the corona itself, and it has been feeding the rest of the solar system for as long as anyone has measured it. In ultraviolet photographs of the sun, most of the disk glows, bright loops and bright arcs. Plasma trapped along magnetic field lines like threads pulled taut between 2 points. But at the poles, large regions go dark, and this is where a dark patch on a star stops meaning what it would mean almost anywhere else. Not because nothing is happening there, because everything that happens there leaves immediately. Scientists call them coronal holes, and the name undersells what they are. A coronal hole is a patch of the sun's atmosphere where the magnetic field, instead of looping back down into the surface, opens straight out into space, giving the plasma trapped along those field lines nowhere to go but away. It is a hole in the sense of a drain, not in the sense of an absence. Matter is not missing there. It is leaving faster than the surrounding image can register its glow. Picture a bathtub with the plug pulled. From above, the water near the drain looks calmer, thinner, less turbulent than the water elsewhere in the tub. Not because it is doing less, but because it is doing the one thing the rest of the water is not. It is on its way out. The polar coronal holes work the same way, funneling plasma outward at close to 800 kilometers every second, fast enough to cross the distance between Earth and the Moon in under 8 minutes. This fast wind, born in the dark, quiet patches at the poles, is not a local curiosity. It is one of the 2 main components of the solar wind that fills the entire solar system. The pressure that shapes every planet's magnetic field, the material that lights up the aurora above your own hemisphere on the nights the timing lines up. Something quiet and dark at the very top of the star reaches you, eventually, as green light in your own sky. There is a second, slower wind too, closer to 400 kilometers a second, seeping out from streamers near the equator rather than draining from the poles. The Ulysses spacecraft spent years in the 1992 and early 2000s measuring both winds directly, sweeping over first one pole and then the other, and found something the equatorial view from Earth could never have shown. Near solar minimum, the calm point in the sun's cycle, fast wind poured from the poles almost constantly, while the slower, more turbulent wind stayed pinned closer to the equatorial belt. The poles, it turned out, were not the quiet end of the star. They were the reliable end, doing the same job over and over while the equator improvised. The coronal holes are not new. Astronomers have tracked them for decades. What is new is watching them shrink, widen, and occasionally vanish entirely as the poles pass through their chaotic, tangled phase. The drain closing for a while, then reopening once the pole settles. And when it closes, the fast wind stops. Not slowly, within a matter of rotations. Nothing about this happens gently for the spacecraft caught downstream. Fast wind and slow wind, moving at different speeds along nearly the same path outward. Turbulent fronts that correlate with the sun the way water bunches up ahead of a slow-moving boat. Those fronts are what most aurora displays trace back to. Not a single dramatic explosion on the sun, but the quiet, unglamorous traffic jam of one wind overtaking another millions of kilometers before either one reaches you. Since Galileo pointed a telescope at the sun in 1610, carefully, through smoked glass, well aware of what direct sunlight could do to an eye, astronomers have kept an unbroken record of sunspots, 4 centuries of observers, generation after generation, sketching, photographing, counting. It is one of the longest continuous scientific records our species has ever produced, longer than most nations have existed in their current form. If you have ever glanced at the sun through eclipse glasses, you are looking at less than 1/10 of what the star actually is. Galileo was not even first. A German astronomer named Christoph Scheiner and a Frisian astronomer named Johannes Fabricius were sketching the same dark blemishes around the same years, arguing, sometimes bitterly, about who deserved credit and what the spots even were. 2 centuries later, a Swiss astronomer named Rudolf Wolf gathered every fragment of that scattered, quarrelsome record he could find and stitched it into a single running count. Still updated today. Still one continuous line stretching back before the founding of most modern nations. For all 400 of those years, every observation was made of the same thin outer skin. The photosphere, the visible surface, the layer where light finally escapes after a journey scientists estimate takes somewhere between 10,000 and 100,000 years to travel out from the sun's core. Scientists confirmed decades ago that the surface is not where the sun's magnetic engine lives. The sunspots, the flares, the poles we finally photographed in 2025, all of it is the exhaust, not the engine. The actual machinery, the layer where rotation and convection combine to generate a magnetic field strong enough to reach past Neptune, sits far beneath the surface most of our 4 centuries of instruments were built to see. We have a 400-year record of smoke, and almost no direct record of the fire making it. Think about what 400 years of the wrong layer actually cost. Every prediction of an active or quiet solar cycle, every model built to anticipate a dangerous flare, every forecast handed to a satellite operator or an airline planning a polar route was built almost entirely on symptoms visible at the surface, extrapolated backward toward a cause nobody could directly confirm. It is a little like diagnosing an illness for 4 centuries using only the patient's temperature, never once being able to examine the organ actually running the fever. None of this makes the 400-year record worthless. Wolf's sunspot count is still the backbone. Every modern solar physicist checks a new measurement against the single longest unbroken thread connecting Galileo's smoked glass to a spacecraft orbiting past Venus. It simply means the thread was always attached to the wrong end of the machine. That fire lives roughly 70% of the way down toward the sun's center, in a thin, impossibly narrow layer most solar physicists now believe is the true engine of the sun's magnetic field. Nobody has ever touched it. Nobody ever will. Physicists gave the layer a name only in the 1,990 seconds, the tachocline, from a root meaning to run at speed, because it is the frontier where 2 very different kinds of motion meet head-on. Above it, the outer third of the sun churns and convects, boiling like water in a pot, each layer free to rotate at its own pace, the differential rotation that leaves the poles 13 days behind the equator. Below it, the inner core rotates as a single, rigid body, locked together the way a bowling ball turns as one piece rather than in independent layers. Between those 2 regimes sits a shear zone only a few thousand kilometers thick, proportionally thinner than the skin of an apple relative to the fruit inside it. If you tried to travel there, roughly 70% of the sun's entire mass would stand between you and the surface before you arrived. And it is here, in that thin skin, that most solar physicists place the origin of the magnetic field itself, the place where fast rotation, slow rotation, and roiling convection twist together tightly enough to generate a magnetic engine capable of reaching every planet in the solar system. Most solar physicists, not all, a smaller camp points instead to a second candidate, a shallower layer just beneath the visible surface called the near-surface shear layer, where old sunspots decay and drag their magnetic remnants toward the poles. Both camps agree the field is generated somewhere inside the churn. Neither can prove their address is the correct one. And the two theories, called the interface dynamo and the Babcock-Layton mechanism, have coexisted, unresolved, for over 3 decades of research. Here's the part that changes everything. Nobody has ever directly observed the tachocline generating anything. The entire theory, called the interface dynamo, is inferred, built from decades of surface observations and mathematical models, never confirmed by a direct measurement of the layer itself, because no measurement of the layer itself is possible with light. The tachocline sits beneath roughly 70% of the Sun's total mass. No photon born there escapes without being absorbed and re-emitted so many times that any information it carried is destroyed long before it reaches the surface. So how does anyone know the tachocline is even shaped the way the models say it is? They don't. Not with certainty. What they have is a different kind of evidence entirely. Not light, but sound. Moving through the body of the Sun the way sound moves through the body of the Earth during an earthquake, revealing the shape of what it passes through by how it bends and how long it takes to arrive. The comparison to an earthquake is not loose poetry. Geologists learned the layered structure of our own planet. The crust, the mantle, the molten and solid cores, almost entirely by timing how seismic waves from real earthquakes bent and slowed as they crossed each boundary. Solar physicists borrowed the exact same trick and turned it on a star, and the technique now has its own name: helioseismology. That sound has been recorded for over 40 years now. The next stretch of tonight is not about the poles at all. It is about a river running through the inside of this star, and the river is moving in a direction nobody's models expected. The sun is ringing, all the time, like a bell that never stops being struck. Turbulent convection near the surface generates millions of overlapping sound waves that travel inward, bounce off the dense interior, and return to the surface as tiny, rhythmic swells, rising and falling by only a few kilometers. Far too small for you to ever see with an unaided eye, but large enough for a sensitive instrument to register as a Doppler shift in the light leaving the surface. Each of those millions of overlapping tones travels a different path through the interior, some skimming just beneath the surface, others plunging almost to the core before curving back. A sound wave slows or speeds up depending on the temperature, density, and motion of the plasma it crosses. The same way a sound moving through cold air behaves differently than the same sound moving through warm air. By recording how long each tone takes to complete its round trip, and combining tens of millions of these measurements from instruments on the ground and in orbit, scientists can work backward and reconstruct a 3-dimensional map of conditions inside a star none of them will ever visit. Picture a doctor tapping on your chest and diagnosing what lies beneath from the sound alone. Then imagine that same trick performed with 1,000 microphones at once, for 40 years without pause, on a body 109 times wider than the planet you are resting on. Ground-based coverage comes from a network called GONG, 6 identical stations spaced around the planet so that as the sun sets over one, it is already rising over the next, keeping an unbroken watch no single location on Earth could manage alone. In orbit, instruments aboard SOHO and later the Solar Dynamics Observatory have logged the same oscillations continuously since the mid-1990 seconds, an unbroken multi-decade recording of a bell no human ear will ever hear directly. Most of what helioseismology has mapped comes from sound waves, called P modes, bouncing through the outer layers. A second, quieter class of oscillation, called G modes, is thought to ripple through the deep core itself, carrying information from a place even sound waves struggle to reach cleanly. Their signal is so faint that for decades most physicists doubted it could ever be measured at all. A French-led team announced a possible detection in 2017, built on more than 16 years of continuous data. And even that claim remains debated. The deepest layer of the Sun may be the one helioseismology can describe least confidently, using the very method built to see past the surface in the first place. The technique is called helioseismology, and it is how physicists first confirmed the tachocline existed at all, how they measured the 13-day gap between the equator's rotation and the poles, and how, more recently, they went looking for the deep current that the interface dynamo theory says should be flowing there, carrying magnetic flux from the poles back toward the equator to begin the cycle again. They did not find quite what the theory predicted. Near the surface, plasma visibly drifts from the equator toward each pole. A slow current a solar physicist can measure directly in the motion of small magnetic features, moving at a walking pace roughly 10 to 20 meters every second. It is called the meridional flow, and for decades the leading model of the Sun's magnetic cycle depended on it working like a conveyor belt, flowing poleward near the surface, plunging downward at the poles, and creeping back toward the equator along the base of the convection zone, deep near the tachocline, before rising again to start the loop over. The conveyor belt idea explained a great deal. It offered a mechanical reason why old magnetic flux from decaying sunspots gets carried to the poles and flips their polarity every 11 years, and why the whole process takes roughly one solar cycle to complete a single full loop, top to bottom and back. The timing matters more than it might first appear. In this version of the dynamo, the speed of the deep return current is what sets the clock for the entire cycle, the conveyor's total travel time determining how quickly old magnetic flux gets recycled into new sunspots at the start of the next one. Speed the conveyor up in a model, and the next cycle arrives early. Slow it down, and the star appears to rest longer than expected between peaks. It is one of the few places in solar physics where a single flow measurement, pinned down precisely, could sharpen a forecast that currently misses by years. Here's what those numbers don't tell you. Nobody had actually measured the deep return current directly. It was assumed, built into the models, because the surface flow demanded some kind of return path to conserve mass, the same reason a bathtub drain needs somewhere for the water to reappear. When helioseismologists finally pushed their sound wave measurements deep enough to look for it, the return flow did not appear where the conveyor belt model placed it. In some measurements, it showed up far shallower than expected. In others, the flow pattern split into multiple overlapping cells rather than one clean loop, changing shape across different phases of the solar cycle instead of running on rails. Not one belt, several, layered, shifting. Stay with that for a moment. A model good enough to reproduce the surface behavior of an entire star can still be describing a mechanism that does not, underneath, resemble the diagram used to teach it. The Sun rewarded decades of careful modeling with a result correct enough to be useful and incomplete enough to remain, in the most literal sense, an open case, filed but not closed. The conveyor is real. Something is carrying magnetic flux from the surface back into the interior. But the tidy, single-loop version, taught in most textbook diagrams, the version most of us absorbed without ever questioning it, may never have been an accurate picture of what this star is actually doing beneath your line of sight. For most of the 20th century, solar dynamo theory rested on a reasonably clean division of labor. Deep in the tachocline, the shear between the rigidly rotating core and the differentially rotating convection zone would stretch and amplify magnetic field lines, a process physicists call the omega effect. Nearer the surface, the decay of tilted sunspot pairs would twist that field further and carry new magnetic flux toward the poles, named for the two solar physicists who proposed it in the 1960 seconds. Combine the two, add the conveyor belt to carry flux between them, and the model reproduced the 11-year cycle convincingly enough that most textbooks treated the question as settled. The meridional flow measurements complicated that settlement considerably. If the deep return flow does not behave the way the conveyor belt requires, then the mechanism moving flux from the surface down to the tachocline is no longer well established. Some solar physicists now argue the dynamo may operate almost entirely within the near-surface shear layer, without needing the tachocline as an amplifier at all. Others argue the tachocline remains essential and the meridional flow measurements are simply incomplete. Distorted by decades of instrumental noise, scientists have not yet fully corrected for. Both camps can point to published, peer-reviewed evidence. Neither can point to a single measurement that settles the disagreement outright. Differential rotation alone, an effect physicists call the omega effect, can stretch and amplify a weak, disorganized magnetic field into a much stronger, organized one purely through shearing, the same way twisting a loose rubber band tightens and thickens the twist without adding any new rubber. Models suggest the tachocline shear could amplify field strength by a factor of hundreds, assuming the shear operates on the field for long enough, uninterrupted, to finish the job. Whether it gets that uninterrupted stretch of time, given everything the meridional flow measurements now put in question, is precisely what remains unresolved. This is not a story about scientists being wrong. It is a story about a boundary between what instruments can measure directly and what can only be inferred. A boundary this star happens to sit almost exactly on top of. You would not notice any of this disagreement in the ordinary sunlight, reaching your skin right now, calm and unremarkable as ever, no matter which theory happens to be correct. Now, here's something that took decades to figure out, even in outline. Horace Babcock proposed the early skeleton of the surface mechanism in 1961, working from sunspot magnetograms and a hunch about how decaying spots might redistribute their magnetic flux. Robert Layton refined the idea 8 years later into something closer to the model still taught today. Neither man had access to a single helioseismic measurement, because the technique itself would not mature for another 2 decades. They built a working theory of the sun's interior using only what the surface was willing to show them, and much of it still holds. Picture 2 mapmakers, each given half of the same unexplored coastline, each drawing confidently, neither able to compare notes with the other until long after their maps were published. That, roughly, is the state of dynamo theory in the years since the meridional flow complicated the simple version most of us were taught. In 2013, a solar physicist named Junwei Zhao led a team using data from the Solar Dynamics Observatory and reported something stranger than a misplaced current. Evidence of 2 conveyor belts. Not one, stacked at different depths and circulating in opposite senses. An inner cell and an outer cell, where the standard models had assumed a single, simple loop. It was the kind of result a career gets built or broken on, and Zhao's team spent years defending the finding against skeptics who suspected instrumental artifacts rather than genuine new physics. 2 different helioseismic techniques, each perfectly respectable, each published in serious journals, currently disagree with each other about what the deep meridional flow is doing. One method, called time-distance helioseismology, tracks how long sound waves take to travel between 2 points on the surface after bouncing off the interior. Another, called ring diagram analysis, studies how local patches of the surface oscillate in 3 dimensions. Both methods rest on the same underlying physics. Applied to the same regions of the same star, they currently produce noticeably different pictures of how fast, and in some cases, in which direction, the deep return flow is moving. Neither team is making an obvious error. The disagreement traces back to how each method handles the faint, noisy signal buried at depth, where the flow speeds involved shrink to a handful of meters per second, whispers compared to the roaring convection above them. Extracting a whisper from that much noise leaves room for 2 careful, competent groups of scientists to reach different conclusions from what is, in principle, the same underlying data. If you asked 10 solar physicists which technique to trust, you would likely walk away with more than 2 answers. We still do not know, with confidence, what the deep return flow looks like. Some years it appears to reach the base of the convection zone in one continuous sweep. Other years, using other methods, it appears to stall far short of that boundary, unable to complete the loop the textbook models require. Not resolved, filed, honestly, under still open, and it may stay there for a while because the instruments capable of settling it decisively do not exist yet, and the ones that might are still just proposals on a whiteboard somewhere. There is a plan, at least. A mission concept studied for years by both NASA and the European Space Agency would place helioseismic instruments far from the equatorial plane, watching the interior from an angle the current fleet cannot manage, closer to the same kind of vantage that finally lets Solar Orbiter photograph the pole itself. Until a mission like that flies, the deep return flow will remain something scientists infer through disagreement rather than measure through consensus. A current everyone accepts must exist somewhere, and nobody can yet point to with a steady hand. It is one of the more forgivable kinds of scientific uncertainty. Not a crisis, just an honest admission that a star can still outpace the instruments built 4 decades ago to read it, the way a river can outrun the surveyors sent to map it, moving on to a new course before the ink on the old map has even dried. Differential rotation, the gap that leaves the poles 13 days behind the equator, was never as simple as one number for the surface and one number for the core. Helioseismology found a third rhythm hiding within the outer few percent of the sun's radius. A thin band right beneath the visible surface where the rotation rate changes rapidly with depth, faster than anywhere else inside the star. Physicists call it the near-surface shear layer, and it behaves almost like a separate clock spinning at its own pace, layered on top of the broader convection zone's differential rotation, which is itself layered on top of the rigid, single-speed rotation of the core. 3 regions, 3 distinct rhythms, stacked inside one star, roughly 1.4 million kilometers across. Imagine you could descend through the star the way a diver descends through water. Stand at the equator's surface, descend a short distance, and the rotation rate has already shifted measurably. Descend further into the bulk of the convection zone, and the rate settles into the broader pattern astronomers have tracked with sunspots since Carrington. Descend past the tachocline into the core, and the rhythm changes one final time, locking into the slow, rigid rotation that has, as far as anyone can measure, remained essentially unchanged for a very long stretch of the sun's life. The star beneath which you are standing does not run on one clock, it runs on at least 3, nested inside each other like the layers of an onion, each keeping its own time, none of them required to agree. The near-surface shear layer was among the very first firm discoveries helioseismology produced, identified in the early 1990 seconds, and confirmed so many times since that almost no one in the field doubts it exists, unlike the still contested deep return flow. What remains strange is the direction of the change. Rotation does not simply slow in one smooth curve from the fast equatorial surface down into the more uniform convection zone beneath it. It briefly speeds up again in the last stretch before the true surface. A small but measurable kink in the rotation profile, folded into a band barely 35,000 kilometers thick, thinner, proportionally, than the layer's own name gives it credit for. Nobody has fully explained why the near-surface layer exists at all, why the rotation needs to shift so sharply in such a thin band rather than blending smoothly from surface to interior. Some solar physicists suspect it is a clue about where the Babcock-Layton mechanism actually operates. Others suspect it is a symptom of something deeper still, a hint that the whole model of clean, separate rotation zones is a simplification the sun never agreed to. Every layer we have described tonight so far, The tangled pole, the 13-day gap, the tachocline, the contested river, this shear layer, sits inside the outer third of the Sunday. The remaining 2/3, the radiative zone, and the core, rotate almost as a single rigid body, quiet and comparatively well-behaved by comparison, at least according to the G-mode evidence nobody can yet fully confirm. The turbulence, it turns out, belongs almost entirely to the parts of the star closest to us. None of this uncertainty slows the sun down. The star does not pause its cycle to wait for solar physicists to agree on where its dynamo lives. Does not hold off on the next flare until the meridional flow controversy resolves. Does not care whether the tachocline or the near-surface shear layer deserves more credit for the magnetic field currently reaching past every planet in this solar system. The processes continue, indifferent to the argument happening in journals about what to call them. That indifference is, in its own way, the most honest thing about this entire stretch of tonight's journey. 400 years of surface observation gave us a magnificent record of symptoms. 40 years of helioseismology gave us a genuinely three-dimensional, if still contested, picture of the interior producing them. And what both records agree on, underneath every unresolved detail, is that the engine that keeps this star alive is not behaving where anyone thought it lived. Not entirely at the tachocline, not entirely near the surface, not fully mapped by either camp studying it. None of this is trivia confined to journals only specialists read. Every satellite operator planning a launch window, every airline dispatcher rerouting a polar flight during a geomagnetic storm, every agency trying to give a week of warning before a dangerous flare, is working from models built on top of exactly this unresolved foundation. The forecast you might one day see on the news, warning of a solar storm approaching Earth, rests on assumptions about an engine two separate groups of scientists still cannot agree on the location of. None of that uncertainty is cause for alarm. It is simply the true shape of where the science currently stands. Closer to an honest map with several blank regions than a finished one, with every coastline drawn in confidently. The blank regions are exactly where the most interesting work in solar physics is happening right now, and where it will likely still be happening long after tonight ends. Some nights, understanding a place means accepting how much of it still resists being fully known, and letting that incompleteness sit there without rushing to paper over it. The sun has been running this engine, whatever its exact shape turns out to be, since roughly 4.5 billion years before anyone existed to draft the paperwork, indifferent then and indifferent now to whether the drafts ever get finished. It will still be running tomorrow, the next unresolved measurement notwithstanding, the same way it ran yesterday, and the day a much younger version of you first learned what the word sunspot meant, long before any of us had reason to wonder what was happening at the poles it never let us see. We drift, for a moment, back to the surface, where the consequences of that hidden argument eventually show themselves in a way that is impossible to miss. Not in a model, not in a heliosismic inversion, but in the poles themselves, failing to flip together the way 4 centuries of assumption expected them to. Every 11 years, on average, the sun's global magnetic field reverses polarity entirely, whether or not you have ever paid it any attention. The magnetic North Pole becomes the South becomes the North. A complete flip physicists have been tracking directly since the 1970 seconds, using a small solar telescope perched above Stanford University, watching the weak, whisper-level field at each pole for decades without missing a cycle. You have already lived through at least a couple of these reversals yourself, entirely without noticing. The reversal is one of the most reliable facts in all of solar physics. What is far less reliable is the assumption most people carry, even inside the field, that both poles flip at the same time. They do not. The reversal itself was first caught in the act by Harold Babcock and his son Horace in the late 1950 seconds. Using a magnetograph the two of them had built by hand a few years earlier, sensitive enough to trace the faint polar field for the first time in history. Harold had spent decades studying the sun's spectrum before the instrument existed. Horace built much of the new electronics that finally made a signal that small, readable at all. When their traces showed the polar field quietly flipping sign near the peak of the solar cycle, neither of them had expected it, and it took repeated seasons of careful, patient tracing before either was willing to trust the reversal was real rather than an artifact of a temperamental new machine. Records kept at that same telescope, the Wilcox Solar Observatory, stretching back to 1976, show the two hemispheres of the sun regularly reversing months apart, sometimes more than a year apart, one pole completing its flip while the other lags behind, still clinging to its old polarity, even as the rest of the star has already moved on. During the transition between cycle 23 and cycle 24, in the early 2010 seconds, the northern pole finished reversing first. The southern pole did not catch up for roughly another year, leaving the sun for months at a stretch with a magnetic configuration that belonged to no clean model at all. Not the old cycle, not the new one, both hemispheres, pointing in ways that refused to agree with each other about which polarity the star was supposed to be in. Not a glitch. A recurring feature of how this star manages the transition, cycle after cycle, for as long as anyone has kept a close enough watch to notice. Smaller lags of only a few months turn up in the transitions before and after that one. Cycle 21 into 22, cycle 22 into 23, each hemisphere consistently keeping its own private schedule rather than a shared one. Hints of the asymmetry go back even further than the Wilcox record. Photographs taken during total solar eclipses throughout the 20th century, back when eclipse expeditions were one of the only ways to see the faint outer corona at all, occasionally showed coronal streamers shaped asymmetrically between the northern and southern hemispheres. A visual clue that the two halves of the star were not perfectly mirroring each other, decades before anyone had the instrumentation to measure why. The Wilcox Solar Observatory measures something almost absurdly small, weaker than any magnet you have ever held in your hand. A polar magnetic field only a few microtesla strong, roughly 100 times weaker than a typical refrigerator magnet, detected across the vast disk of the sun using a technique called the Zeeman effect, where the presence of a magnetic field splits a single spectral line of light into two closely spaced lines. The gap between those two lines reveals the field's strength. Their relative brightness reveals its direction. Watching that faint signal patiently, rotation after rotation, for close to 5 decades now, is how scientists first noticed the lag was not a one-time anomaly. It showed up across multiple cycles, to varying degrees, the northern and southern hemispheres, treating the 11-year deadline as a rough suggestion rather than a synchronized appointment. The lag during the cycle 23 to 24 transition was the largest well-documented case, but smaller lags of a few months appear again and again throughout the observatory's entire record. The sun, it turns out, does not experience its own magnetic cycle as a single event happening to the whole star at once. It experiences two separate, loosely coordinated events, one per hemisphere, that happen to average out to the familiar 11-year rhythm most people learn about in school. The signal is so faint that for years after the observatory began operating in 1976, researchers debated how much of the noise in the traces was real solar variation and how much was simply the instrument straining at the edge of its own sensitivity. Decades of patient repetition, rotation after rotation, year after quiet year, eventually separated the signal from the noise convincingly enough that today the polar field measurement recorded near solar minimum, the quiet stretch just before a new cycle begins, is treated as one of the single best predictors available of how strong the next cycle will be. A weak polar field near minimum tends to forecast a weak cycle ahead. A strong one tends to forecast a stronger cycle. And the relationship has held up, imperfectly but usefully, across every cycle since the rule was proposed. It is one of the few genuinely reliable rules solar physicists have, precisely because it comes from measuring the poles directly, rather than inferring their state from the tangled, noisier activity happening everywhere else across the visible disk. The idea that the polar field could serve as an early warning for the next cycle was proposed as far back as 1978 by a solar physicist named Kenneth Shatton, at a time when the Wilcox record was barely 2 years old and far too short for anyone to confirm it with any confidence. It took roughly 3 more decades of patient, unglamorous data collection, cycle after cycle logged without fanfare, before the pattern held up across enough repetitions for the method to be trusted by anyone outside the small group of researchers who had first proposed it, let alone by the wider, understandably skeptical community of forecasters who would eventually come to rely on it. Considerably less symmetry than the phrase 11-year cycle quietly implies, and less than you were probably taught, if this ever came up in a classroom at all. For most of a solar cycle, the sun's global field behaves close enough to a simple bar magnet that the two-pole description works fine for almost every purpose. One pole positive, one pole negative, field lines arcing between them the way they do around any ordinary magnet you might hold in your hand. That simple picture collapses during the lag between hemispheres. With one pole already reversed and the other still holding its old polarity, the large-scale field briefly stops behaving like a simple dipole altogether and starts behaving like something closer to a quadrupole, a 4-part structure, as though the star had grown a second pair of magnetic poles it had no use for and no clear plan to remove. Here's what most people completely misunderstand about a magnetic reversal. This is not a metaphor stretched past its usefulness. Physicists measuring the shape of the field during these transition months actually need higher-order mathematical terms, quadrupole terms, to describe what the data shows, terms that are close to irrelevant during the calmer years, further from the reversal. A useful way to picture the difference: a simple two-pole field, viewed from a great distance, looks like the arcs drawn around a single bar magnet, a north arcing cleanly over to a south. A 4-part quadrupole field looks more like 2 bar magnets stacked with opposing ends touching, producing twice as many regions where the field points inward or outward, before the star settles back into the simpler shape. Spacecraft stationed a short distance from Earth, sampling the solar wind streaming past continuously, register the difference directly. During the messy transition months, typically lasting a year to 18 months, they cross far more magnetic sector boundaries per rotation than the calmer years produce, sometimes flipping polarity 2 or 3 times where a single clean crossing would normally do. The complexity does not stay politely confined near the poles either. It propagates outward, reshaping the heliospheric current sheet you heard about earlier tonight into something far more folded and unpredictable than the clean ballerina skirt the calmer years produce, right at the exact moment spacecraft and satellites most need the shape to behave. How long the messy, 4-part configuration lasts varies unpredictably from one cycle to the next. Some transitions resolve within a few months, the star settling back into its simple 2-pole shape quickly. Others, like the drawn-out transition into cycle 24, stretch the confusion out for well over a year, the extra months adding directly to how long the folded, unpredictable version of the heliospheric current sheet persists for everything orbiting nearby, from the smallest research satellite to the crewed missions passing through the same tangled space, none of them able to simply wait out a mess measured in months rather than minutes, or to reroute around a maze that changes shape faster than a mission plan can be redrawn. Uncomfortable, and also unavoidable. This appears to be how the star has always made the transition, cycle after cycle, long before anyone was measuring it closely enough to be bothered by the mess. The shape of the heliospheric current sheet is not a cosmetic detail confined to diagrams in a physics paper. It determines how easily charged particles from outside the solar system, cosmic rays born in the death throes of stars that exploded long before the sun existed, can find their way in toward the inner planets. A folded, tilted current sheet acts like a maze, forcing incoming cosmic rays to travel a longer, more tangled path before they reach Earth, deflecting many of them away entirely. A flatter, calmer current sheet opens straighter corridors, letting more of that ancient radiation slip through. Physicists even classify entire solar cycles by which magnetic polarity state they occupy, because the two states let measurably different amounts of cosmic radiation through to the inner solar system, a pattern confirmed by decades of neutron monitor data recorded at stations scattered across this planet. The asymmetry between the poles, the lopsided lag we just described, feeds directly into how folded that maze becomes and for how long. Neutron monitor stations, ground-based detectors first built in the 1950 seconds at sites like Climax in Colorado and Oulu in Finland, have logged this modulation continuously for most of a century now, and the swings are not subtle. Cosmic ray intensity reaching the inner solar system can vary by 15 to 20% between the quiet years of solar minimum, when the maze runs more open, and the tangled years around solar maximum, when the folded current sheet blocks more of the incoming radiation. Astronauts and high-altitude aircrew, spending long hours above the thickest part of the atmosphere's shielding, absorb a measurably higher dose during the open years than the tangled ones, one of the few places where the abstract shape of a magnetic maze translates directly into a number a flight crew's dosimeter can register. You are standing at the end of that maze right now, breathing air this radiation constantly passes through, a background hum of particles older than the sun itself, arriving in slightly different amounts depending on which polarity state the star currently occupies and how tangled its current sheet has become. Most of it is stopped by the atmosphere above your head long before it reaches you. A small amount is not, and has been part of the ordinary background of your entire life without you ever noticing the difference. The same particles that shape a flight crew's radiation dose can, on rare occasions, flip a single bit inside a satellite's onboard memory, a fleeting electrical error engineers call a single event upset. Small enough to fix with a reboot, and consequential enough to plan entire redundant systems around. Spacecraft designers build in redundancy specifically because the folded maze above your head is never completely impenetrable, only ever more or less so, depending on which phase of the 11-year rhythm the sun currently occupies, and which hemisphere finished its half of the argument first, a detail no engineer, however careful, can fully plan around in advance. The maze reshapes itself every 11 years. You have already lived through several versions of it. Solar cycle 24. The same cycle whose reversal left the two hemispheres out of step for the better part of a year likely spans a stretch of your own life, whether or not you noticed it passing and turned out to be unusually weak overall. One of the quietest cycles recorded in roughly a century of continuous sunspot counting. Fewer sunspots, lower peak activity, a maximum that, by several measures, barely qualified as a maximum at all compared to the robust cycles common through most of the 20th century, the kind older solar physicists had spent entire careers treating as the reliable baseline. Nobody had confidently predicted the weakness in advance. Several of the models built specifically to forecast solar cycle strength, models incorporating exactly the kind of meridional flow and dynamo assumptions described earlier tonight, pointed toward a stronger cycle instead, closer to the 20th century average. The minimum preceding cycle 24 was itself unusual, stretching on longer than any minimum recorded in nearly 100 years, stretch after stretch of entirely spotless days, piling up through 2008 and 2009, while solar physicists waited, increasingly uneasily, for the new cycle to visibly begin. Satellite measurements during that same stretch recorded the solar wind's pressure at its lowest point of the entire space age, the heliosphere itself measurably shrinking as the unusually quiet sun pushed less forcefully against the interstellar material, pressing in around it. A contraction later confirmed independently by the two Voyager spacecraft still sailing outward toward that same boundary. Was the unusually long lag between hemispheres a cause of the weak cycle, a symptom of the same underlying weakness, or simply a coincidence riding alongside it? Solar physicists still argue about the ordering. Nobody has settled which came first, and a single cycle, however carefully measured, is not enough data to settle it. The weak, messy Cycle 24 became something of a turning point inside the field, not because it revealed a single flaw to fix, but because it revealed how many independent models had converged on the same wrong answer. Confidence built from many contributors agreeing is not the same as confidence built from being right, and Cycle 24 forced a fairly public, somewhat uncomfortable reckoning with that difference. By the time forecasters prepared their outlook for the following cycle, the panel convened to issue it deliberately avoided settling on one dominant model, favoring instead a blended, consensus range wide enough to admit how much remained honestly uncertain. It was a quieter, more modest kind of prediction than the confident number issued before Cycle 24, and in its own way, an admission that the engine beneath this star had earned that modesty the hard way, one missed forecast at a time, across a field that had spent a full 11-year cycle relearning, in public, exactly how much it still did not know about the star it studies more closely than any other. That uncertainty carries directly into the next question worth asking tonight. If one weak, lopsided cycle could catch an entire field of forecasters off guard, what does that say about how much anyone can really promise about the cycle still to come? The one you happen to be living through right now. Two hemispheres, reversing on their own loosely related schedules. A current sheet reshaping itself into a tangled maze each time the reversal runs long. A cycle that quietly broke from the 20th century's pattern without asking anyone's permission first. None of it happened suddenly, and none of it required you or anyone else living an ordinary life beneath this star to notice at the time. All of it happened slowly enough and quietly enough that most of it went unnoticed by anyone who was not specifically watching a faint magnetic signal from a small telescope at Stanford. The natural question, the one every forecaster eventually has to answer out loud, is simple. If scientists cannot yet predict when the two hemispheres will finish flipping in step, or how weak or strong a coming cycle will turn out to be, how good is anyone's forecast really? Some systems resist prediction not because they are poorly understood, but because they are exquisitely sensitive to details too small for any instrument, present or future, to fully capture the same basic quality that makes Earth's own weather hard to forecast more than a week or two out. Solar physicists disagree about how much of the sun's unpredictability falls into that category, and how much is simply a gap current instruments will eventually close. Both possibilities remain live, and both would explain nearly everything observed so far. What would it take to close that gap? Solar physicists increasingly point to the same answer from two different directions at once. More time spent watching the poles directly, the way Solar Orbiter finally allowed in 2025, combined with longer, cleaner helioseismic records reaching deeper into the interior than the current 40-year archive can manage. Neither exists yet in the form scientists would need. Both are, at least, finally being pursued in the same decade. After centuries where nobody could examine the poles or the interior at all, that is, in its own way, a form of progress worth sitting with for a moment. The same way you might sit with an unfinished puzzle, rather than sweeping the pieces away. Not a solved mystery, but a meaningfully better set of tools finally aimed at a very old question. Progress of that kind rarely arrives as a single breakthrough announced all at once. It arrives the way most of tonight's discoveries have arrived so far, in decades of unglamorous, continuous watching, one faint magnetic trace at a time, one helioseismic inversion at a time, one slow orbital tilt at a time, until enough small measurements finally stack into a picture nobody could have assembled from any single one of them alone. The pattern is old, 4 centuries old in fact, and long before anyone had a magnetograph, a spacecraft, or even the concept of a magnetic pole, one particular stretch of that 400-year record went almost entirely silent, decades of it. And nobody watching the sun at the time understood what the silence meant or how long it would last before the sunspots simply returned. The next part of tonight is not about the poles and not about the interior. It is about 4 centuries of predictions and one long, unsettling silence in the historical record that no model built since has ever fully explained. In 2006, a year that may fall somewhere inside your own memory even if you were not paying attention to sunspots at the time, a panel of solar physicists convened by NASA and NOAA sat down to do something scientists rarely attempt in public. Issue a single, specific number predicting how strong the next solar cycle would be years before it began. The panel split almost exactly down the middle. Half the group, working from a flux transport dynamo model built on the same conveyor belt assumptions described earlier tonight, predicted cycle 24 would be one of the strongest in decades, its peak sunspot count rivaling the powerful cycles of the mid-20th century. The other half, working from the polar field precursor method, the same one built on Wilcox Solar Observatory data, predicted the opposite. A weak, unremarkable cycle, one of the quietest in 100 years. 2 teams, both using established, peer-reviewed methods, looking at the same star, reached forecasts that differed by roughly a factor of 2. One of the strong cycle predictions carried real institutional weight. Published that same year in a major journal built on a detailed flux transport simulation that traced magnetic flux through several previous cycles before projecting the next one confidently upward. A vocal minority, including researchers who had spent years mining the Wilcox polar data directly, argued just as publicly that the simulation was extrapolating past what the deep flow measurements could actually support. The disagreement became public enough that the panel, unable to fully reconcile the 2 camps, eventually resorted to publishing a wide compromise range rather than a single confident number, an admission built directly into the forecast that the models underneath it did not agree with each other. There was no way, in 2006, to know which half of the panel to believe. Both sides published their reasoning. Both waited. Cycle 24 arrived weak. Not moderately weak, among the quietest cycles in the entire century-long instrumental record, far closer to the number the precursor camp had proposed than the number the dynamo modelers had defended. The failure was not a failure of effort or intelligence. Every physicist on that panel had access to the same decades of surface data, the same emerging helioseismic record, the same historical sunspot count reaching back to Galileo. What they did not have, and still do not fully have, is agreement on where the engine generating that cycle actually lives, whether the tachocline or the near-surface layer deserves the deciding vote, whether the meridional flow completes its loop the way the textbook diagram assumes. A forecast is only as good as the model behind it, and the model behind half of that forecast rested on an assumption about a deep return current nobody, to this day, has ever directly and conclusively measured. The panel had, without quite saying so out loud, staked one of its 2 competing predictions on exactly the unresolved river described earlier tonight. And the river, when the cycle finally arrived, sided with the camp that had trusted the poles over the models. A small, quiet vindication for anyone who had ever argued that measuring something directly, however faint, beats inferring it cleverly. Between roughly 1,645 and 1,715, 70 years you would very likely not have survived to see the end of, had you been born at the start of it. The sun did something it has not repeated with anything like the same severity in the entire 400-year sunspot record. It went almost completely quiet. Astronomers of the era, using the same basic telescope technique Galileo had pioneered decades earlier, recorded stretches of years, Not days, not months, years, with barely a sunspot visible anywhere on the disk. A British astronomer named Edward Maunder, working at the Royal Observatory in Greenwich 2 centuries later, was the one who dug back through the scattered historical logs and pieced the silence into a single, coherent episode. Long after most of his contemporaries had dismissed the old records as simply incomplete, rather than an accurate account of a quiet Sunday. Maunder published his case in 1894 and again in 1922. And for decades afterward, most solar physicists treated the idea as a curiosity rather than a serious finding, an old astronomer's hunch about records too patchy to trust. It took until the 1970 seconds when an American astronomer named John Eddy cross-checked the sunspot gap against entirely independent evidence. The radiocarbon trapped in tree rings from the same centuries for the scientific community to accept that the quiet stretch had genuinely happened. The period now carries Maunder's name, the Maunder Minimum. 70 years is not a short pause. It is longer than most human lifespans of the era that lived through it. An entire population who could have been born, raised children, and died without ever once seeing the kind of active, spot-covered sun that every generation before and after them took for granted. Nobody living through it understood what was happening to their star, because nobody yet understood that stars had cycles to interrupt in the first place. The 11-year rhythm itself would not be identified until the following century, by a German pharmacist and amateur astronomer named Heinrich Schwabe, who spent 17 years searching the sun for an entirely different, undiscovered planet, and stumbled onto the cycle instead. What actually silenced the sun for 70 years remains one of the least understood events in the entire historical record, precisely because it happened before anyone had the instruments now used to study a decade-like cycle, 24 inches, such detail. No magnetograph existed to trace the polar field through those decades. No helioseismic archive can be run backward far enough to listen for what the interior was doing while the surface stayed quiet. The best evidence available is indirect, second-hand, and centuries removed from the event itself, pieced together from sketchbooks, correspondence between astronomers who doubted each other's eyesight, and the faint chemical residue the sun's own quiet left behind in ice and wood. Whatever silenced the engine for 70 years did not damage it permanently. The sun resumed its ordinary rhythm afterward, cycle following cycle much as it had before, as though the machinery had simply been idling at a lower setting rather than failing outright. Whether that idling traced back to the tachocline, the near-surface layer, or some combination neither camp has fully articulated, is precisely the kind of question this entire stretch of tonight keeps circling back to, unresolved, not for lack of trying, but for lack of a direct enough instrument. The 70 quiet years of the Maunder Minimum overlapped, roughly, with the coldest stretch of a centuries-long period historians call the Little Ice Age. Decades of harsher winters across Europe, frozen rivers that rarely froze solid before or after. Famous paintings of ice fairs held on a frozen Thames that would be unrecognizable to anyone standing on the same riverbank today, market stalls and bonfires set up on ice, thick enough to carry the weight of an entire crowd. For weeks at a stretch, an entire seasonal economy built on a kind of winter. Modern Londoners rarely, if ever, experience anymore. The overlap is real, and it is tempting, and it is also more complicated than a single cause and a single effect. A quieter sun does emit slightly less energy, measurably less, though the total difference is small, a fraction of a percent at most, not obviously large enough on its own to freeze a river that had never frozen solid within living memory. Volcanic eruptions during the same centuries pumped enough ash into the atmosphere to dim incoming sunlight independently. And several of the largest, most disruptive eruptions in the historical record happened to cluster inside the same 70 years. Shifts in ocean circulation patterns, unrelated to the sun at all, compounded the cooling further, redistributing heat away from the exact regions where the harshest winters were recorded. Untangling how much of the cooling belongs to the quiet sun, how much to the volcanoes, and how much to the ocean is still an active area of climate research. One that requires reconstructing 3 separate, overlapping natural systems from proxy evidence centuries old, rather than from any direct instrument reading. Climate scientists today generally treat the quiet sun as one contributing factor among several, not the single explanation the overlap in timing seems to invite. The honest version of the story is less satisfying than the dramatic one. A star that went unusually quiet at almost exactly the same centuries, a colder Earth needed several separate explanations, working together to produce the winters people actually lived through, none of them sufficient alone, all of them compounding at once. What the overlap does confirm, regardless of how the contributions eventually get divided by careful reconstruction, is that the engine hidden beneath the sun's surface does not only shape space weather and satellite forecasts. Left quiet long enough, its influence reaches all the way down to a frozen river, and to the people who once walked across it without any idea their star had gone quiet at all. You will not feel the next grand minimum, if one arrives in your lifetime, the way those crowds felt the ice beneath their boots. The connection between a quiet sun and a cold winter is loose enough, and diluted by enough other factors in the modern climate system, that it would arrive as a subtle statistical nudge, rather than a dramatic, unmistakable freeze. But the underlying mechanism, an engine occasionally running quieter than usual for reasons still not fully understood, would be exactly the same mechanism that iced the Thames 3 centuries ago. Every dynamo model used to forecast a coming solar cycle, including the ones that split so sharply over cycle 24, is trained and tested against direct magnetic measurements collected only since the 1,950 seconds, barely 70 years. A single lifetime, out of a star that has been running its cycle for roughly 4.5 billion years. Cosmogenic isotopes. Carbon-14 preserved in tree rings and beryllium-10 preserved in ice cores. Both produced when cosmic rays strike the upper atmosphere at rates that shift with solar activity, extend the record much further back than any telescope or magnetograph ever could, connecting directly back to the same cosmic ray modulation described earlier tonight, the folded maze that a lopsided current sheet either opens or closes. A more active sun blocks more cosmic rays and leaves less of the isotope behind in that year's tree ring or ice layer. A quiet sun blocks fewer, and the isotope accumulates more heavily, leaving a legible, if indirect, fingerprint centuries after the fact. That extended record shows the Maunder minimum was not a singular event. A similar, slightly less severe quiet period, called the Spura minimum, appears in the isotope record roughly 2 centuries earlier. Another, the Dalton minimum, shows up around the turn of the 19th century, mild enough that direct sunspot counting had already resumed by the time it arrived. Reaching further back, the isotope record suggests grand minima of varying depth recur every few centuries on average. An irregular but persistent rhythm layered on top of the more familiar 11-year cycle. Grand minima, it turns out, are a recurring feature of this star's behavior, not a one-time historical fluke. But here's the question that keeps solar physicists awake at night more than any single forecast. No dynamo model in current use was built with a grand minimum inside its training data, because no grand minimum has occurred since the instruments capable of feeding a model directly have existed. Every forecast issued today is, in a very real sense, extrapolating confidently from the calm centuries and hoping the quiet years stay hypothetical. It is a little like teaching someone to predict earthquakes using only a few decades of seismographs from an unusually stable stretch of a fault line, then asking that same model to anticipate the 1 century in 500 when the fault finally lets go. The physics might still hold. The data the physics was tuned on simply never included the event the forecast most needs to get right. The rare decade rather than the common one the exception the model was never asked to rehearse for. This is not a reason to distrust solar physics as a field. If anything, it is a reason to respect how openly the field admits it. Few areas of science volunteer, on the record, that their most important predictive tool has a documented blind spot exactly where the stakes are highest, and fewer still keep funding the missions and monitoring stations built specifically to shrink that blind spot rather than quietly hoping nobody notices it is there. They will not stay hypothetical forever. The isotope record makes that much clear. Even if it cannot yet say which future decade the calm arrives in, whether that decade turns out to be one you happen to be living through, or one long after you are gone. Every object we have ever built to study the sun, up to and including the spacecraft that finally photographed its pole, has studied the star the way you have studied it your entire life, from a distance, gathering light and particles that have already traveled millions of kilometers and changed along the way. In 2021, a spacecraft named Parker Solar Probe became the first to cross into the corona itself. Passing through the Alphen critical surface, the boundary where the sun's magnetic field finally loses its grip on the outward flowing solar wind and lets it escape freely into the solar system. Below that boundary, the wind is still tethered, still tied to the star closely enough to be dragged around by its rotation. Above it, the wind is free, no longer answering to the sun the way a stone stops answering to a sling the instant it releases. Parker Solar Probe crossed that exact threshold repeatedly, dipping in and out of the true edge of the star, rather than merely observing it from beyond, a boundary that itself moves closer to or farther from the visible surface depending on how active the sun happens to be at the time. No spacecraft had done this before. Not Ulysses. Not any of the missions that photographed the poles decades later. Reaching the corona required a heat shield capable of surviving temperatures near 1,400 degrees on the sun-facing side, while the instruments tucked behind it, only meters away, operated near room temperature, an engineering problem that delayed the mission's design for years before the shield materials existed to solve it. A gap between one side of a single spacecraft and the other, larger than most industrial ovens, are built to survive at all. The corona at that boundary reaches temperatures over 1,000,000 degrees, hundreds of times hotter than the visible surface far beneath it. A genuine, decades-old puzzle in itself. How a surface at roughly 6,000 degrees sits underneath an atmosphere that much hotter, defying the ordinary rule that heat radiates outward and cools with distance from its source. Parker Solar Probe did not answer why the corona is so hot. A puzzle that remains as open today as it was before the mission launched. It brought back something else entirely. Something in the structure of the wind itself that nobody who designed the mission had specifically gone looking for, discovered simply because the spacecraft finally flew close enough to see it directly, rather than infer it from a distance. The same lesson the poles taught in 2025 had already taught the corona a few years earlier. That proximity reveals what distance can only guess at. It took a spacecraft built to survive conditions no prior mission had attempted to finally notice a feature of the solar wind that had been streaming past Earth, undetected in this much detail for the entire history of space exploration. The instruments that eventually caught it were not searching for anything unusual. They were simply, for the first time, close enough to see the ordinary wind clearly. The solar wind, once free of the sun's grip, is supposed to behave in a fairly simple way. The same wind that is, at this moment, streaming past you and every other planet in the solar system. It streams outward in mostly straight lines, carrying the sun's magnetic field with it, like a flag trailing behind a moving ship, the field lines gradually curving into the long spiral shape predicted by theory since the 1,950 seconds. Parker Solar Probe found something folded into that outward stream the simple model never predicted. Sudden, sharp kinks in the magnetic field, shaped switchbacks where the field briefly reverses direction entirely before snapping back, sometimes doubling the local speed of the wind for a few seconds as it whips past. The switchbacks arrive in clusters, not scattered randomly, and their frequency changes depending on how close the spacecraft happens to be to the base of the corona. Not gradual, not a smooth drift back to normal. The field simply flips, holds, and flips again, hundreds of times, within a single hour, close to the Sun, thinning out the farther the spacecraft travels from the star, until far enough out the wind finally settles into the smooth spiral the textbooks describe. Where do the switchbacks actually come from? The leading explanation traces them to narrow magnetic funnels at the base of the corona. Threaded between the edges of the same coronal holes described earlier tonight, tiny regions where convection at the surface jostles the open field lines, hard enough to send a kink rippling outward, the way flicking one end of a rope sends a wave travelling down its length. Not every physicist accepts that explanation fully. Some suspect the switchbacks form much farther out, shaped by turbulence in the wind itself, rather than by anything happening at the surface. A third group suspects both mechanisms operate simultaneously at different distances, and that the clean single origin story every camp would prefer simply is not how this particular puzzle is going to resolve, a possibility that satisfies nobody's preferred version of a tidy answer, and that may, in the end, turn out to be closer to correct than either single origin story on its own. The debate has not settled, and Parker Solar Probe continues gathering closer passes, closer to the fire, in the hope that enough close data will finally reveal where in this star's atmosphere the kinks are actually born. Each new perihelion brings the spacecraft a little nearer to the surface than the pass before it, the mission's own trajectory tightening in on the same unresolved boundary the rest of tonight keeps circling back to. Whichever explanation eventually wins, the switchbacks matter for a simple reason. They carry energy, extra, unaccounted for energy folded into the ordinary solar wind, and that energy has to come from somewhere. Tracing it back to its source is, in a very real sense, the same project every discovery tonight has quietly been circling, one layer of the star at a time, one instrument generation at a time, from a magnetograph built by hand in the 1,950 seconds to a heat shield engineered to survive a star's own atmosphere, all of it eventually arriving, as the ordinary wind now passing quietly by, wherever you happen to be resting. 4 discoveries were promised at the start of tonight, and each of them now sits somewhere between confirmed and still argued about. The pole, photographed for the first time in 2025, turned out to be magnetically confused rather than the clean two-sided magnet generations of diagrams assumed. The interior current, the deep return flow the flux transport models require, remains measured differently by different techniques, never yet pinned down with the single, steady number a forecaster could build a confident prediction on. The 2 hemispheres, reversing on their own loosely related schedules, keep producing exactly the kind of lopsided, tangled transition period that turns a simple 2-pole star into something closer to 4 poles for months at a stretch. And the forecasting record, humbled by Cycle 24's very public split decision, has settled into a more modest, consensus-driven habit of admitting uncertainty rather than projecting false confidence. None of the 4 threads is resolved. All 4 are real, measured, published, argued over in ongoing journals rather than settled decades ago and filed away. That is worth sitting with for a moment. An object visible to the naked eye on any clear morning, studied longer and more continuously than almost anything else in science, still capable of producing 4 separate open questions serious enough to occupy entire careers, fund entire missions, and split entire forecasting panels down the middle, decades into an era most people, understandably, assume finished mapping this star a long time ago. The 400 years of sunspot counting gave us patience. The 40 years of helioseismology gave us depth, The 5 decades of polar magnetic monitoring gave us the asymmetry. The handful of years since a spacecraft finally left the flat plane, every mission before it had been confined to, gave us the picture that started tonight's journey in the first place. And the even smaller handful of years since another spacecraft first touched the corona directly gave us a wind that refuses to behave the way a century of theory predicted it would. Each layer of evidence built on the one before it, and each layer complicated the simple story slightly further rather than resolving it. What remains is the part most nights like this one save for last. Not what the sun is doing to itself, deep beneath a surface no eye will ever fully see, but what all of it is doing to you right now. Whether or not you had ever thought about a tachocline or a switchback before tonight began, none of the 4 discoveries stay confined to journals and observatories. Every one of them, the confused pole, the contested river, the lopsided reversal, the humbled forecast, eventually reaches down through the layers of space between this star and the surface you are resting on, arriving as something closer to home than any of it first appears, close enough to touch the ordinary shape of a night like this one, and close enough to touch the body listening to it. Every discovery described so far tonight, the confused pole, the contested river, the lopsided reversal, has lived somewhere between a spacecraft and a research paper, distant enough to feel like someone else's problem. The sun does not stay that distant. It reaches your body directly, and it has been doing so every day of your life without asking permission. Nearly every calorie of energy inside you arrived first as sunlight, captured by a plant somewhere in the chain of meals that became you, converted from light into stored chemical energy, through a process this star makes possible simply by shining. Trace any meal backward far enough, and the trail ends at the same source. Not a farm, not a field, but the fusion happening right now in the sun's own core, roughly 8 minutes of travel time away. Photosynthesis converts a percentage of incoming sunlight so small it borders on absurd, typically only 1 or 2% of the energy actually striking a leaf into stored chemical energy. And yet, that thin trickle, multiplied across every leaf, every ocean-dwelling plankton cell, every blade of grass on the planet, has been enough to power nearly every living thing for roughly 3.5 billion years. Longer than the sun has generated a magnetic field stable enough for scientists to study in any real detail. Your skin runs its own smaller conversion, turning a specific narrow band of the same sunlight into vitamin D, a molecule the body cannot manufacture any other way in meaningful quantities, tied closely enough to mood, immune function, and bone density that entire populations at far northern latitudes adapted lighter skin over thousands of years. Simply to capture more of a resource, this star doles out unevenly by latitude. None of this required the sun to behave simply or predictably, or without the tangled poles and contested interior described earlier tonight. The star has been inconsistent at the poles and reliable at the surface simultaneously for the entire 4.5 billion years. Your body's chemistry has depended on the second half of that arrangement without ever needing to understand the first. Closer still, a cluster of cells behind your eyes. Cells that do nothing but measure the particular wavelength and intensity of daylight reaching them, feeds that measurement directly to a small structure deep in your brain that sets the timing of nearly every other process in your body. When you feel alert, when you feel tired, when hormones rise and fall, when your body temperature dips low enough to help you fall asleep in the first place. That clock did not evolve in a vacuum. It evolved answering to this exact star, tuned across hundreds of millions of years to the particular rhythm of a G-type star, roughly 4.5 billion years old, orbited by a planet tilted at roughly 23 degrees. You are, in the most literal sense available, an instrument the sun has been calibrating since long before you were born, tuned to a rhythm you did not choose and cannot fully override, no matter how many blackout curtains you hang or how late you push a night like this one. In September of 1859, roughly a century and a half before you were born, a British astronomer named Richard Carrington The same astronomer who would soon document the sun's differential rotation was sketching a cluster of sunspots when he witnessed something no one had recorded before. A sudden, blinding brightening within the sunspot group itself. Lasting only a few minutes, a flare so intense he assumed his own equipment had failed. It had not failed. Carrington was not alone in seeing it either. An amateur astronomer named Richard Hodgson, observing independently only a short distance away, recorded the same sudden brightening at nearly the same moment, and the two men's matching, independent accounts were what convinced the Royal Astronomical Society the event was real rather than an instrumental fluke. Carrington had witnessed the most powerful solar flare in the observational record, and the coronal mass ejection that followed reached Earth in a little over 17 hours, far faster than the several days a typical eruption takes to cross the same distance. Pause on that number. 17 hours across 93 million miles. Telegraph systems across Europe and North America, the most advanced long-distance communication technology of the era, failed and sparked. Some operators reporting electric shocks through their equipment, some lines continuing to transmit messages, even after being disconnected from their batteries, running on current induced directly by the storm itself. Aurora, normally confined to polar latitudes, were reported as far south as the Caribbean, bright enough in some locations that observers described being able to read a newspaper by their light in the middle of the night. Gold miners in the Rocky Mountains reportedly woke and began preparing breakfast in the middle of the night, convinced from the brightness alone that morning had already arrived. The event now carries Carrington's name, though it was the sky itself, visible across 3 continents, that made it impossible for anyone living through it to ignore long before a single scientist understood what a coronal mass ejection even was. Nobody in 1859 connected the bright light in the sky to the failing telegraph wires directly, not with any confidence. The two effects, one overhead and one running through a cable underground, seemed to belong to entirely separate categories of event. It would take decades of accumulated observation and eventually a name for the mechanism itself, before scientists understood that the storm in the sky and the storm in the wire were the same storm, arriving through 2 different kinds of evidence at once. The Carrington event remains the benchmark against which every storm since is measured, not because a stronger one is impossible, but because nothing since has combined its intensity with a direct hit on Earth. Ice core records, the same cosmogenic isotope evidence used to trace the Maunder minimum, hint at least one earlier storm, roughly 1,000 years before Carrington's telescope existed, that may have rivaled or exceeded it, a reminder that the historical record humans happen to be watching during is a narrow slice of what this star has actually produced. Nothing on the scale of the Carrington event has struck Earth directly since, though a comparably powerful storm in 2012 crossed the exact orbit Earth occupies, missing our planet by a matter of days purely because of where Earth happened to be positioned in its orbit at the time. A storm of that scale striking today's infrastructure directly, rather than the glancing blow Earth received in 2012, would reach satellites, undersea communication cables, and GPS timing systems that telegraph operators in 1859 could not have imagined needing to worry about. Systems you rely on every day without ever thinking about the star making them possible in the first place. A geomagnetic storm in March of 1989, considerably smaller than the Carrington event, induced electrical currents strong enough to trip protective relays across the Hydro-Quebec power grid in Canada, plunging roughly 6 million people into darkness within about 90 seconds. A blackout that lasted 9 hours in the depths of a Canadian winter. And this is where it stops sounding like a problem for satellites alone. The mechanism is not exotic. A geomagnetic storm changes the shape of Earth's magnetic field rapidly enough to induce an electric current in anything long, conductive, and grounded, precisely the description of a modern power transmission line stretching for hundreds of kilometers. The induced current is small compared to what the line was built to carry, but transformers are sensitive instruments, and a current oscillating in a way the equipment was never designed to handle can push a transformer toward overheating or trip a protective system built to prevent a fire rather than absorb an unusual signal. Power grids today carry far more capacity than they did in 1989, serve far more people, and in many regions still run through transformers built decades before anyone fully appreciated how vulnerable that infrastructure was to a storm of the kind Carrington documented in 1859. Large power transformers of the type most vulnerable to this kind of surge are not something a utility keeps sitting in a warehouse. Custom-built, often shipped from overseas manufacturers, a single replacement unit can take more than a year to design, build, and deliver an uncomfortably long timeline if a severe storm damaged several at once across a regional grid. Regulatory bodies overseeing North America's power grid began requiring utilities to plan explicitly for geomagnetic disturbances only after the 1989 blackout forced the issue, decades after the underlying physics had already been understood well enough to predict the risk. New standards now require the largest utilities to model their vulnerability to a range of storm strengths and report the results, a direct regulatory descendant of 9 dark hours in Quebec. Engineers have made real progress, hardening the most critical parts of the grid since then. Installing devices that block the slow, storm-induced currents without interfering with the much faster alternating current the grid actually runs on. Nobody in the field claims the job is finished, and nobody can yet say with confidence how a modern, far more interconnected grid would handle a storm on the Carrington event scale, rather than the comparatively modest one that hit Quebec. The interconnection itself cuts both ways. A more tightly linked grid recovers faster from a small, localized fault, sharing the load across a wider region the moment one part fails. The same interconnection also gives a single, sufficiently severe storm more pathways to travel through, tripping relays across state and even national borders in the kind of cascading failure the 1989 storm hinted at on a smaller regional scale. None of this is presented tonight to alarm you before sleep. It is presented because the maze described earlier, the folded current sheet, the cosmic rays, the switchbacks, was never only an abstraction floating somewhere between the sun and Earth. It runs, eventually, straight into the wiring beneath the room you are resting in right now. However many layers of engineering stand between that wiring and the star that first set the current moving. Roughly 1 million miles closer to the sun than Earth itself, at a gravitational balance point called L, one where the pull of the sun and the pull of the Earth roughly cancel out, a small satellite named DSCOVR sits permanently between you and the star, watching the solar wind stream past it before that same wind ever reaches home. DSCOVR was not originally built for this, conceived in the late 1990 seconds as an Earth observation mission, shelved for years afterward, for reasons that had nothing to do with its scientific merit. It eventually launched in 2015, repurposed as the closest thing space weather forecasting has to an early warning radar. When a coronal mass ejection passes the satellite's sensors, controllers on the ground get a window of roughly 15 to 60 minutes, depending on the storm's speed, before the same wave of charged particles reaches Earth's own magnetic field. 15 to 60 minutes is not long, not much more than the time it might take you to fall asleep tonight. It is, however, long enough to warn airlines to reroute a polar flight, long enough for grid operators to reduce load on the most exposed transformers, long enough for satellite operators to switch sensitive instruments into a safer configuration before the storm actually arrives. None of it prevents a Carrington-scale event from being dangerous. All of it is considerably better than the 0 minutes of warning telegraph operators had in 1859. The satellite has no way of predicting which storms are coming days in advance, only of confirming one has already left the sun and is now approaching fast. Longer-range warning still depends on the same contested models, the same disputed meridional flow, the same forecasting record humbled by Cycle 24 described earlier tonight. The tower watches closely. It still cannot see very far ahead. A newer companion mission now shares the same vantage point, launched specifically to improve on DSEOVR's aging instruments and extend the same brief warning window a little further. Neither spacecraft changes the deeper problem described throughout tonight. Better eyes at the last possible moment do not resolve a disagreement about the engine generating the storm in the first place. They simply make sure nobody is caught as unprepared as a 19th century telegraph operator ever again. The watchtower is a recent addition to a very old habit. Long before any satellite sat at that gravitational balance point, sailors and farmers watched the sky itself for warning. Aurora and unusual light treated as omens long before anyone had a mechanism to explain them. The instruments have changed almost beyond recognition. The basic posture, watching the sky for a warning about what the sun is about to do next, has not changed at all, only moved 1,000,000 miles closer to the source and traded a farmer's uneasy glance at the horizon for a satellite that never once looks away. Day or night, storm or calm, patient in a way, no human watcher standing outside in the cold ever could manage for long, relaying its warning back down the same 1,000,000 miles of empty space in a matter of seconds. Nearly everything described tonight about the sun, the differential rotation, the churning convection, the buried shear layer generating a magnetic field through motion rather than through any fixed magnet, has a close cousin running beneath your own feet. Roughly 3,000 kilometers down, Earth's outer core churns as a vast ocean of molten iron and nickel, convecting, rotating slightly differently from the layers above and below it, generating our planet's magnetic field through the same basic family of physics solar physicists call a dynamo. Earth's dynamo is calmer than the sun's. Its reversals spaced not every 11 years, but over intervals ranging from tens of thousands to millions of years, so infrequent that human civilization has never witnessed one directly. But the underlying mechanism, motion-generating magnetism rather than magnetism existing as some fixed, permanent property of the material itself, is the same insight solar physicists spent the 20th century applying to the star above. The evidence for Earth's past reversals comes from an unlikely source: solidifying volcanic rock and seafloor basalt lock in the direction of the magnetic field at the moment they cool, preserving a record geologists can still read millions of years later. Long parallel stripes of alternating magnetic polarity, discovered on the ocean floor in the 1,960 seconds, turned out to be one of the decisive pieces of evidence confirming that entire continents drift, a discovery that reshaped geology as thoroughly as helioseismology later reshaped solar physics. The most recent full reversal, called the Brunhes-Matuyama transition, happened roughly 770,000 years ago, long before any human being existed to notice. The field did not vanish during the transition or leave Earth unshielded for that stretch, as some popular accounts imply. It weakened, wandered, occasionally split into multiple weaker poles rather than one clean pair, and eventually reorganized into the reversed configuration that persisted afterward. A slow, messy process that geophysicists studying it can only reconstruct in outline, never in the kind of resolution a live spacecraft could provide for an event happening today. Every compass needle that has ever settled toward north was answering a process every bit as dynamic, every bit as unresolved in its finer details. As the tachocline debate described earlier tonight, geophysicists still argue about exactly how Earth's core sustains its own field, how the inner core's slow growth affects the convection above it, whether the field's next reversal, whenever it comes, will announce itself gradually over thousands of years or arrive faster than anyone currently expects. You have spent your entire life trusting a needle that points toward an argument scientists are still having, on a planet running a smaller, slower version of the same unresolved machine described at length tonight, floating in the magnetic exhaust of a star running a bigger one. Two dynamos, nested one inside the other's influence, neither fully understood, both keeping you safe in ways too constant to notice. The smaller one shielding you from the larger one's worst moods, the larger one supplying the very energy your body runs on in the first place. Solar Cycle 25. The cycle following the weak, lopsided Cycle 24 described earlier tonight, arrived stronger than the consensus forecast expected, its peak activity exceeding the modest, hedged prediction issued after the field's public reckoning with its own overconfidence. Forecasters had, if anything, learned humility a little too well, undercorrecting in the opposite direction after Cycle 24 had punished overconfidence so publicly. Sunspot counts climbed faster than the official outlook anticipated within the first few years alone, and several geomagnetic storms during the cycle's rise arrived stronger than the modest forecast had prepared anyone to expect. The lesson solar physicists drew from that undercorrection is almost the same lesson Cycle 24 taught in the opposite direction. A forecast built by averaging two disagreeing camps into a cautious middle is not automatically safer than trusting either camp fully. It is simply differently wrong. And which direction the error runs in only becomes obvious once the cycle has already arrived. Cycle 26. Expected to begin its rise sometime in the following decade, quite possibly within a stretch of your own future you have not planned for yet, remains almost entirely unpredictable using the tools described tonight. The polar field measurements that will matter most have not finished accumulating. The meridional flow's true shape remains contested between competing helioseismic techniques. Whether the two hemispheres will reverse together or drift apart again, the way they did heading into Cycle 24 will not be knowable until the reversal is already underway, and the Wilcox Observatory's faint traces start showing which pole is moving first. A newer approach has entered the field over the past several years, feeding decades of magnetic and helioseismic data into machine learning systems rather than physics-based dynamo equations. Early results are mixed, sometimes matching traditional forecasts, sometimes diverging from them in ways nobody has fully explained yet. One more voice added to a conversation that already included two competing camps in 2006. Solar physicists will make a prediction anyway, because forecasts are useful even when imperfect, and because a wide, honest range beats no estimate at all. But the honest version of that future forecast, the one implied by everything described tonight, is closer to an admission than a promise. Nobody yet knows, and the engine making the decision is still running somewhere beneath a surface no one has fully mapped. Whatever Cycle 26 brings, the same institutions that split in 2006 and undercorrected before Cycle 25 will convene again, compare notes again, and publish a range wide enough to survive being wrong in either direction. That is not a failure of nerve. It is what an honest forecast looks like when it is issued by people who have already been surprised twice by the same star in two different directions within two consecutive cycles. Somewhere in the years ahead, the poles will begin their next slow argument with each other. The current sheet will fold into its own tangled shape again, and a new panel of solar physicists will sit down and attempt, once more, to say in advance what a star that has resisted every previous attempt at prediction is finally going to do, while you, most likely, go on living beneath it without checking the forecast at all. Every discovery tonight has been framed, more or less, as a search for a location. Which layer holds the true dynamo, the tachocline or the near-surface shear? Which pole reversed first, where the switchbacks are actually born? 400 years of steadily improving instruments, each one getting a little closer to a single hidden room where the real machine supposedly sits waiting to be found. Here is the reorganizing thought worth carrying out of tonight, rather than into it. There may not be a single room. The 13-day gap between the equator and the poles is not a flaw sitting beside the real engine. It is raw mechanical stress the engine runs on. The disagreement between the tachocline and the near-surface layer is not two wrong guesses waiting for one correct answer. It may be two genuine contributors, operating in something closer to an argument than a partnership. And that argument may be the field's actual origin. The hemispheres falling out of step are not a glitch interrupting an otherwise unified star. They may be evidence that unified was always the wrong word for what this star does. Consider how many separate teams of scientists tonight's journey has quietly assembled. The team that finally photographed a pole, the team measuring a river 2 different ways and getting 2 different answers, the team that caught one hemisphere arriving late to its own reversal, the team that split down the middle over a single number in 2006. None of them were wrong about their own measurement. Each of them was accurately describing one true piece of a machine that may simply refuse to live in one place. It is a strange kind of comfort, if you let it be one. A 4.5 billion-year-old star, studied longer and more carefully than almost anything else in the sky, still cannot be reduced to a single tidy address tucked neatly into the tachocline, or the near-surface layer, or one pole, or one hemisphere, or one clean number a panel could agree on in advance. It may be the most accurate description available of what a star actually is. Most things worth understanding resist a single tidy address. A body is not seated in one organ. A season is not caused by one single factor, but by an axial tilt, an orbital distance, and an atmosphere, all acting together. A star, it turns out, follows the same pattern everything complicated seems to follow. The closer you look, the more the explanation spreads out across every layer at once, rather than collapsing into the one clean room early instruments hoped to eventually find. Tonight leaves that thought where it belongs, unresolved, carried forward, rather than argued to a close. Some nights are not for finishing an argument, they are for learning its shape well enough to rest inside it anyway. The engine that keeps this star alive was never missing from any diagram. It was the argument between the diagrams. All along, you began tonight beneath a star whose poles no one had ever seen, a simple fact stated plainly before any of the rest of it unfolded. You now know why that was true for 400 years, and why it stopped being true only recently, not because anyone lacked curiosity, but because leaving the flat plane every planet shares costs more fuel than almost any mission has ever been willing to spend. Until one finally was. You know, the pole itself turned out to resemble an argument caught mid-sentence far more than the calm, orderly diagram in a textbook. 2 polarities refusing to resolve, a magnetic field still deciding what it wants to be. You know that argument reaches down through a 13-day gap in rotation, through a shear layer a few thousand kilometers thick, through a river that 2 different instruments still cannot agree on the shape of, through 2 hemispheres that have never once, in 50 years of careful watching, reversed at exactly the same moment. None of that uncertainty makes the star less reliable in the way that matters most tonight. It has burned, steadily enough to matter, for 4.5 billion years, through a 70-year silence, through cycles too weak to predict and cycles too strong to fully explain, through every disagreement scientists have ever had about where its engine actually lives. It will burn through tonight as well, indifferent to whether you are awake to notice. Exactly as it has burned through every other night you have ever fallen asleep beneath it without a second thought. You began tonight not knowing any of this. You now know more about the star above you than nearly anyone who lived and died before the year 2025. More than Galileo, more than Carrington, more than the physicists who split down the middle over a single forecast in 2006. Because you arrived after the pole was finally photographed, after the river was finally measured twice and disagreed with itself, after the case had accumulated into something a single night could actually hold. That is not a small inheritance. It took 4 centuries of patient counting, 40 years of listening through sound waves, 5 decades of chasing a signal fainter than a household magnet, and a spacecraft's slow climb out of the only plane every mission before it had ever occupied, just to reach the point where all of it could be told. In order, in the space of one night, to someone falling asleep. Nobody hands you an inheritance like that and asks anything of you in return. You do not need to remember the exact name of the tachocline by morning or recall which helioseismic technique disagreed with which, for any of it to have done its quiet work tonight. The knowledge does not need to be held tightly to matter. It only needed somewhere to land. And it landed here, in the last stretch of a night, already halfway to morning, in a mind already loosening its grip on the details in order to rest. Consider the arc of everything since Galileo first turned a telescope toward danger and lived to sketch what he saw. 4 centuries of counting, 40 years of listening for sound waves inside a body of plasma, 5 decades of tracing a signal 100 times fainter than a refrigerator magnet, and finally, only months before tonight, a spacecraft patient enough to climb out of the only angle any instrument had ever occupied. Each generation added a layer the one before it could not see. And each layer made the star slightly less simple than the last generation believed. That is not a story of scientists failing to finish their work. It is the ordinary shape of understanding something enormous. Never complete, always revised, always a little stranger, the closer anyone manages to look. The star above you tonight is the same star it was in Galileo's century, unbothered by 400 years of being studied, unbothered by whichever theory currently wins the argument about where its magnetism lives. It has one habit it has never broken, through every silence, every reversal, every forecast that missed. It rises, it sets, it reaches you. Whether or not anyone has settled, where inside it the light begins. Every layer described tonight, the tangled pole, the buried shear, the contested river, the lopsided hemispheres, was uncovered by people willing to keep looking at something already assumed to be fully understood. That willingness, more than any single instrument, is the actual thread connecting Galileo's smoked glass to a spacecraft photographing a pole 4 centuries later. The star rewards nothing about that patience directly. It simply keeps being there, layer beneath layer, for as long as anyone keeps choosing to look closer. We've drifted tonight through a pole nobody had seen until months ago, down through a river no 2 instruments can fully agree on, past 2 hemispheres keeping their own private time, and into a forecasting record humbled enough to have finally learned some honesty. Together, we've wandered from the very top of a star down into a sheer layer no light will ever escape from, and carried all of it back out again into the ordinary dark where you are resting now. None of it was ever really about the sun alone. It was about the star that grows your food, sets your clock, shields you in a maze of its own folded making, and still, after 4 centuries of careful watching, keeps enough of itself hidden to remind anyone paying attention how much size and time can hold. Every layer we followed tonight, from the confused pole down to the sheer no light escapes, eventually arrives somewhere. Tonight, it arrived in you. If your eyes feel heavy, let them close. That was always the point of a night like this one. Not to finish the argument, but to let it settle into something you can rest inside of. Unresolved and still, somehow, enough. If this felt like home, leave a comment when you wake up, and tell us which discovery from tonight followed you into your dreams. If you're still here, still awake, the next chapter is waiting. Whenever you're ready for it, the universe will still be here when you wake up. So will we. Good night.